Today in this video, I would like to give you a brief overview of the course, and I want to start section 1.2, Data Basics. So in the overview, my goal is to define statistics and what we do when we say we're calculating statistics. So to do that, I need to start with a motivating example, and this is my motivating example. Consider the following research question. What is the average age of an American? So let's start off by asking ourselves, what is the population? What is the group of people I'm interested in? So the population, the definition in statistics is the entire group of individuals or objects being studied. And so in this research question, my population is all Americans. I am looking at all Americans and I'm trying to calculate their average age. So let's assume that this circle with a bunch of dots represents the population, all Americans. And I know there's about 340 million Americans. That's a lot. And I can't make dots for every single American, but that's the idea. We're going to think of this as the population. Now, in theory, how could we calculate the average age of all Americans? Well, what we would need to do is we would need to go around and ask every single person how old they are. So maybe we start with Tom. We say, how old are you? He says 37. And then we would need to make like a spreadsheet or something, write it down somewhere to collect all of this data. Then we go to Susie, Jessica, and ask them their ages. And we would need to make a spreadsheet with about 340 million entries, and all of them being ages. And then once we have all that data, now there's different ways to calculate the average, but one of the most common ways is to add all those numbers together and then divide by the total amount of numbers. So that's how we would do it in theory. But what are some challenges we might face when we try to calculate this number? Well, the first challenge is going around and finding every single American. There's so many Americans. And even if we could figure out where all the Americans were, to go around and ask all these Americans their ages would take time. It would take a lot of time, especially if it's just one person asking. So we could hire a bunch of people. Like if you think about the census, the US government hires people to go to different houses and ask them questions or something. So sort of like that, we could hire people to go around and ask everybody their age, but that costs money. People don't do this for free. You would have to pay them. So we face basically two problems, time and money. So how can we get the information we're looking for without actually asking every single American their age? Well, one thing we could do is create a sample, which is a subset of the population being studied. So here I just have a circle and I've chosen 4 random dots. One of the problems we're going to consider in this class is how big should a sample be and how do we choose our sample? How do we make it representative of the population and reduce bias? So suppose we construct a sample of 100 Americans. So these 100 Americans, we can ask them how old they are. This is a lot less data to work with. It's more manageable. We can go around and ask everybody how old they are, and we can put that in a spreadsheet, and then we can calculate the average. So let's just say that we have a sample of 100 Americans, and these 100 Americans have an average age of 43. We call this number 43 a statistic. So what is a statistic? It's a single number or piece of data that summarizes the sample. So in our sample, we have 100 different ages, but we can summarize that list of ages by spitting out one number, and that's the average. We could use, for example, the mode, the range, the mean. There's a lot of different statistics we could use. Statistics is just one number that summarizes the whole sample. So the average would summarize all of these ages. So the word sample starts with an S, and the word statistic starts with an S. Statistic describes the sample. Now, our goal is to estimate the average age of all Americans. It wasn't to find the average age of just a sample. How can we find the average age of all Americans? And would that age be the same as the age from the sample, the average age from the sample, 43? What do you think? The answer is no. Why is it no? Because if I chose a different sample of a different 100 Americans, they would have different ages. And then if I average their age, I might get something else, like I might get 38 as the average. And a different sample might give me a different number. It turns out that whatever average you get is not going to be the exact number for the population. Now, a parameter is a single number or piece of data that summarizes the population. Parameter starts with P, population starts with P. Parameters is a piece of data that summarizes the population, while statistic summarizes the sample. Now, finding the average age of an American is a parameter, and we are never going to find this parameter. It's impossible because we have to ask every single American to find the exact number. And we don't have the time or the money to do that. So in this class, we're going to learn how to use statistics to make educated guesses about parameters. So for example, this number 43, let's say that was the average age of a sample of 100 Americans. What we're going to do is we're going to learn how to make a net of possible values that the true population parameter, the true average age of an American, will live inside. So we're going to learn how to add and subtract some numbers from 43 that will give us a range. Maybe the number we have to add and subtract is 13, and that would give us a range of 30 to 56. And we would be able to say something like the true, where I would say like a percentage confident, we're 95% confident that the true average age of Americans is between 30 and 56. So all of this language we're going to learn later on in the class. So some problems we have to answer, some questions we have to answer include the following, and this is things that we're going to learn in this class. How do we choose our sample? So we need to make sure that our sample is representative of the population. So for example, if you want to find the average age of an American, you wouldn't just pick students from a high school and let that be your sample, because their average age may not be representative of the population. So we're going to talk about how to reduce bias, how to choose our sample. That's something we're going to do this week and part of next week. Another question you might have is, how many samples do we need? How large should our samples be? Is there a minimum size and maybe a maximum size? And once we have a sample, how do we collect data from that sample? Like, do we give them a survey? Do we do an experiment? It depends on the question that we're interested in. Also, how much data should we collect? Should we just collect, for example, in this particular research question, should we just find the average age of Americans? Should we also figure out the color of their eyes, their heights, their weights? Maybe there's something else we would be interested in, so maybe we should collect more data. And we also would like to know, how do we organize that data? How can we visualize data? We're going to see pie charts and bar graphs, all of that kind of stuff. Okay, so what is statistics? Statistics is the science of collecting, organizing, summarizing, and analyzing data from a sample to draw conclusions or answer questions about a population. So again, we have a population, we're trying to answer a question about it, but it's too big, there's too much data, or maybe we can't get all of the data. And so what we do is we get a sample, and then we analyze that sample and try to use whatever we get from that sample, any statistics, to determine what the true parameters or answer the questions we were interested in about the population. That is our goal in this class. So we're going to learn the foundations of all of this. This class is divided into 4 parts. So for the first 2 weeks, we're going to learn about data collection. We'll learn how to build a sample that's representative of the population and how to collect data from that sample. Then, weeks 2 and 3, we'll talk about descriptive statistics, which is where we'll learn how to summarize and interpret the collected data. So you already have the data. How can we extract information from it? That's what we're going to do in weeks 2 to 3. And then our ultimate goal is to take these statistics and use them to build nets that will tell us something about the population. So weeks 4 through 8, we have to learn some foundations for how we can do this. So it involves probability and probability distributions. So we'll look at that through weeks 4 through 8. And then we'll learn how to draw conclusions from data. So from the sample, we'll be able to draw conclusions about the population. That's called inferential statistics. And that will be from week 8 to the end of the semester. So there's 4 parts of this class. And right now we're starting with data collection. So let's take a look at a sample. In a sample, each individual is referred to as a case or observation. So in this particular sample, I have 4 dots. So there would be 4 cases, or you could say there's 4 observations in the sample. Characteristics of the cases are called variables. What is a variable? A variable can take different values for different individuals. So let's look at an example. Suppose our population is students at ECU. Let's come up with some examples of variables for these students. So I want something that can change depending on the student, like eye color. Eye color is a variable. If I had a set of 30 ECU students, one person might have brown eyes, one person might have blue eyes, one person may have green eyes. So this is something that changes depending on the individual. And so that is a variable. Another example would be height. Somebody may be 5 feet 4 inches, somebody might be 6 foot tall, and so on. It depends on the person. Let's see, another variable, maybe shoe size. That would depend on the person, so it would change depending on the person. Let's see, let's do one more. Maybe the state they were born in. That would be a variable. Some people would be born in North Carolina. Some people might be born in Alabama or Washington State or Oregon or so on. It depends on the person. So a variable is different than a statistic. So a variable changes depending on a person, but a statistic is taking all of the data and it doesn't depend on a person. It's like averaging the data or something like that. We'll see more of that later. Our focus right now is on variables, and there's 2 basic types of variables, numerical variables and categorical variables. Let's take a look at numerical variables first. So what is a numerical variable? It's a variable that can be expressed in terms of numbers, and not only does it have to be numbers, but it makes sense to add, subtract, or take averages. Numerical variables are also known as quantitative data. Now, categorical variables, on the other hand, are variables that put the cases, remember, cases are the individuals in the sample. It puts the cases into groups or categories. This is also known as qualitative data. and it doesn't make sense to add, subtract, or take averages. Now, might be a little confusing, but there can be categorical variables that have numbers in them. It's just that you can't add, subtract, or take averages, and we'll see an example in a little bit. So let's jot down some examples of both numerical and categorical variables. Eye color. So if we're thinking about students at ECU, if we have a sample of students, eye color is a variable. This is a categorical variable because it's brown, green, blue. Those are eye colors that are words. So it's definitely not a numerical variable. You can't add brown plus blue and get something in between. Okay. Height. Height is a numerical variable. Weight, that is a numerical variable. Telephone number. Telephone number is a categorical variable. Now, the reason it's categorical is because it doesn't make sense to add two telephone numbers together or to add them and divide by 2 to find an average. So this is how I try to keep them straight. If you get confused, just because it has numbers doesn't make it a numerical variable. You have to be able to add, subtract, and take averages. So telephone number is a categorical variable. Another one that could contain numbers in it would be like a student ID number. That would be a categorical variable and not a numerical variable. Number of siblings. That is a numerical variable. A letter grade in English class, like if you made an A, A minus, B, C, D, so on, that's a categorical variable. Shoe size, that is a numerical variable. The number of pet cats someone has, right? Somebody could have 0 cats, 1 cat, 2 cats. That's a numerical variable. The hometown where they grew up, that would be a categorical variable. And one more, the level of education, like whether they had a high school diploma, an associate's degree, a bachelor's degree, that would be a categorical variable. So remember, these are variables because they change depending on the individual. Okay, let's focus on the numerical variables. So with numerical variables, we can split them into 2 categories. They're either continuous or discrete. So what is a discrete numerical variable? Well, it's a number with clear jumps. The data is countable and it can be finite or infinite, but it cannot take on every possible value between any 2 possible numbers. So like the number of siblings someone has, they either have no siblings, 1 sibling, 2 siblings, 3 siblings. These jumps are clear. You can't have 2.78 siblings. That just doesn't make sense. So that would be an example of a discrete numerical variable. While a continuous numerical variable is the opposite of that. It's data that can have an infinite number of values between any two points, such as the real numbers. The way that you can keep continuous variables straight is you have to measure it. Like imagine you have to use a scale or a ruler. That would be a continuous numerical variable. So which of those variables in the last slide are discrete and which are continuous? Let's start with numerical and discrete. So the number of pet cats and the number of siblings, those are discrete numerical variables. While height, weight, and shoe size, those are all things we have to measure, and so those are continuous. So if you think about it, if you think about somebody's height, let's say you use a ruler and they're 5 feet 4 inches. If I use a more precise ruler, they might be 5 feet and 4.2 inches. Like actually nobody is a height like exactly 5 feet 4 inches. They're always going to be, there's going to be some rounding there. So you're going to have, it's going to take on multiple numbers, if that makes sense. So shoe size as well. If you measure the length of your foot, depending on the ruler, you might get two different numbers, but they're going to be rounded. Weight, like if I have a better scale, like if you weigh yourself at home versus maybe at a doctor's office, you're going to get a more precise weight, and it can take on values like 0.2, 0.3. This is continuous. So again, discrete, clear jumps, and continuous is measurable. Okay, let's focus on categorical variables. Categorical variables can be split into nominal and ordinal categorical variables. Look at the word ordinal. It has the word order in it, and that means we can put the data in some kind of natural order. So ordinal data has a natural order or rank. In a way, it's similar to numbers, and the mode and median make sense on these variables. While nominal categorical variables is data without a natural order or rank. I think this is easier to understand when we look at the variables and try to classify them into ordinal or nominal. Okay, so of those variables we mentioned earlier, ordinal categorical variables would be level of education and letter grade. If you think about letter grades, there's a natural order, right? A is better than B, which is better than C, which is better than D, and so on. Level of education. High school diploma comes before associate's degree, which comes before bachelor's degree. There's a natural order to that. While eye color, brown eyes don't come before blue eyes, and they don't come before green eyes. Telephone numbers, it doesn't really make sense to list them in a particular order. Or hometown, you could put like alphabetical order on this, but it's not a natural order. You're just defining an order. While level of education, letter grade, that is something that has a natural order. Another example would be like people who have a cold. The level of symptoms like mild, moderate, severe, that would be something with a natural order, and that would be ordinal. So I want to make a note that putting a variable in alphabetical order does not count as a natural order, okay? So sometimes students get that confused with ordinal categorical variables. Okay, and again, here's just a chart of all the types of variables. So all variables can be classified into numerical or categorical. If you have a numerical variable, it's either continuous or discrete. And if you have a categorical variable, it's either nominal or ordinal. Okay, moving on, how can we organize data? I mentioned earlier that we can put data into a spreadsheet, which in statistics is sometimes called a data matrix. And the rows are cases or the observations, so people in your sample and the data from those people. So each row is a person and their values for variables, while the columns are the variables like age, eye color, those are columns, and you can see that they're variables because they change depending on the person. So researchers often look for relationships between two or more variables. We say that two variables are associated if they show some connection with one another. Scatter plots help us visualize if two numerical variables are associated. So whenever we use scatter plots, we're always working with numerical variables. So maybe we think shoe size and height of a person are related in some way, and we can visualize that with a scatter plot. Now, a scatter plot is just a bunch of dots, and each dot represents a person and two variables associated with that person. Let me give you a few examples. So here I have a bunch of data on heart disease, And each little dot represents an individual. And a dot for an individual tells us their cholesterol level along with their blood pressure. So let's look at this, let's look at this dot all the way in the left-hand corner, near the bottom, the most left dot. So this is an individual who has a blood pressure of about, let's say, 100 or so. It's a little bit less, you can see, than 110. And they also have a cholesterol level, which is the y-axis, of above 120. And then let's look at the furthest dot to the right. So way over here, this person has a blood pressure level of 160. And it looks like their cholesterol level is above 160. So the dots represent people and their blood pressure and cholesterol levels. Now, somebody, by visualizing this, they can answer the question, is high blood pressure associated to high cholesterol levels? Like, is there a relationship between high blood pressure and cholesterol levels? And it looks like in this graph, there is an association. And I would describe that association as linear, meaning it looks kind of like a line. These dots don't exactly line up on a line, but if from afar away, it looks like it's going up with a positive slope. So I would say a positive linear association. So you could say a positive linear relationship, a positive linear association, a positive linear correlation. Here's another set of variables we could be interested in: the weight of a car and its city fuel consumption, or MPG. So each little dot represents a car, and the x-axis is its weight, and the y-axis is the miles per gallon it gets in the city. So looking at this graph, I would say there seems to be a negative linear association, meaning that not all the dots line up on a line, but it's kind of close to a line, and the slope of that line would be negative. Okay, is there an association between height and exam scores in college algebra? So here we have a bunch of students, we have their heights and their exam scores, and we don't even have the numbers, we just have a bunch of dots. Just looking at the dots and thinking about height and exam scores, would you think there's an association or a relationship between those two? I would say no, and there doesn't seem to be a real pattern here. So I would say there's no association. So variables that are not related in some way are called independent. Let's look at one more example. Here I have a bunch of dots that represents different counties, and the percentage of people living in poverty is the x-axis, and the y-axis is the population change over 7 years in that county. And it really doesn't matter what the axes are. What I'm really interested in is the association. What do we see? I see a linear association, but it's a straight horizontal line. Now, if you think about it, that means that no matter what x is, it doesn't depend on, like y doesn't depend on x. So even if we have a linear association, if it doesn't have a positive slope or a negative slope, then it's no association. So here are some examples of things you'll see in a scatter plot. You may see a positive linear association, a negative linear association. You see this bottom left-hand corner, we have something that looks like, it's not quite a line, it's a curve. And we would say that there is an association here, but it's nonlinear. And the last graph, which is just a bunch of dots that doesn't seem to have a pattern, is no association. And if we ever have a vertical line or a horizontal line, that's also no association. Okay, if two variables are associated, does that imply that a change in one variable causes a change in the other? So the answer to this is no. Association does not mean causation. So here I have a scatter plot of a store, and the x-axis is the number of sunglasses sold on a particular day, and also the y-axis is the ice cream sales on a particular day. So for example, this first dot all the way on the left, on a particular day, they sold about 110 sunglasses and also about $200 worth of ice cream. Now, if you look at this association, it does seem positive and it does seem linear. But the thing is, there is an association, but that doesn't mean the number of sunglasses sold. If we increase the amount of sunglasses, that means ice cream sales is also going to increase. There's some other variable related to these two, which is like the time of year, how hot it is. If it's in the summertime and it's hot and it's sunny, maybe it's the sunniness of the day and the heat that would increase the number of sunglasses being sold along with the amount of ice cream being sold. So this is an observational study. We'll talk more about it later on this week and into next week. But observational studies cannot show causation. There's another variable that influences how many sunglasses are being sold, and also how much ice cream is being sold. How about this one? Is the weight of a car related to its city fuel consumption? Let's think about that sentence versus does the weight of a car affect its city fuel consumption? So we saw the scatter plot earlier, and on the bottom we have the weight of the car. That's the horizontal axis, and the y-axis is the city miles per gallon. And we said that this is a negative association, a negative linear association. So we can answer the first one, the first question. We said, yes, it is related. There's an association. But can we prove that the weight of a car affects the city fuel consumption? We cannot prove it with this graph. We'll have to do some more digging, and we'll talk about that later. But just by looking at a graph, we cannot look at a scatter plot and say, yes, it affects, the weight of a car affects city fuel consumption. But it might. And so when one variable might affect another variable, we can label them in a particular fashion. We call one an explanatory variable and the other one a response variable. So if we suspect one variable affects the other, then we can label them in the following way. Like I would think the weight of a car might affect the miles per gallon. So the explanatory variable is the weight of a car, and the response variable is miles per gallon. So we think the weight of the car explains the miles per gallon. The miles per gallon is responding to the weight of the car. Okay, so that's how I would keep them, understand the two terms, try to keep them straight. Now, you wouldn't think that the miles per gallon a car gets would affect the weight of the car. It is the weight of the car, how heavy it is, would affect the miles per gallon. So at this moment, we can't prove that the weight of the car affects the miles per gallon. But if we suspect this, we can label these variables as explanatory variable and response variable. Note, the act of labeling does not guarantee a causal relationship. Causal relationship means one variable causes a change in the other. Okay, I'm going to give you 4 examples, and I'll give you a couple of minutes. We'll look at the first 2, and what I would like you to do is label which variable is the explanatory variable and which is the response variable. So maybe pause the video and see if you can figure out which is the explanatory variable and which is the response. Okay, so the first problem says the amount of time spent studying for a statistics exam and the grade on the statistics exam. Is there maybe a causal relationship here? I would say yes, and I would say the amount of time you spend studying, there's a chance that that would affect the grade you get on that exam. So I would say the explanatory variable is the time spent studying for the exam, and the response variable is the grade on the exam. Now for the second problem, the weight in kilograms and the height in centimeters of a person. I would think the taller a person is, the more mass they take up, and that might affect their weight. So if there is, now I'm not saying that it does, height influences weight, but if it did, the explanatory variable would be height in centimeters of a person, while the response variable would be the weight in kilograms of that person. Let's try two more. So you want to decide if there is an explanatory response situation. Could one variable cause a change in the other? And if so, what is the explanatory variable and what is the response? So pause the video and see if you can figure out which one is which. Okay, for problem 3, it says the yield of corn in bushels per acre and the inches of rain in the growing season of corn. I wouldn't think that corn influences rain. I would think rain influences corn. So my explanatory variable would be inches of rain in the growing season of corn, and my response variable would be yield of corn in bushels per acre. Now for the last problem, a student scores on the SAT math exam and the SAT verbal exam. I wouldn't think that your math scores would influence your verbal scores or the vice versa. I would think that those would be separate. I think if you studied for the exam, let's say you studied the math section, you probably studied the verbal section as well. So there might be an association. People who did well on the math exam may have done well on the verbal exam as well, but I don't think one causes a change in the other. So I would say that the explanatory variable and response variable does not apply in this situation. Okay, so that covers section 1.2. You should be able to do some homework. I think there's 3 homeworks that I'm going to assign for this section. And so good luck, and if you have any questions, feel free to send me an email or to write on the discussion board.